This is lecture 6 of Logika računalništvu, and we're going to continue looking at predicate logic today. So last week we looked at algorithmic problems associated with predicate logic, and we found that the situation was much less satisfactory than it is in propositional logic, which is not so surprising given that predicate logic is quite a bit more expressive and correspondingly more complicated. So just to summarize what we found, we found, not necessarily in exactly the same order as last week, but we found, maybe it is, I don't remember, but we found that satisfiability is undecidable. And we defined what that meant. For predicate logic. Validity is also undecidable. But we can get a yes answer when it is valid. We just can't get the no answer. So that's what's called semi-decidable. Actually, satisfiability, we can get the no answer, but not the yes answer. But anyway, so it's sort of co-semi-decidable. But anyway, validity is semi-decidable. But one way to get a yes answer for satisfiability is to only look for finite models. So that takes us to finite satisfiability, and we saw that that too is semi-decidable. But again, not decidable. This time we can't. Finite validity is, in this case, undecidable. So, so finite satisfiability is also undecidable, but it's semi-decidable at least. So finite satisfiability is also semi-decidable. So if we want to see, do we have a finite structure, we can in principle do that, but it's as I tried to explain last week, it's a very combinatorially complicated or combinatorially explosive blind search basically, and it's not the kind of it's not the sort of problem you can really try to run on a computer. Try to find does there exist a finite model, an arbitrary sized finite model. Well, at least not in that way. So what we're going to see today is that there is actually a way that we can run this that's better than a blind search, but we can only do that if we put a bound on the search, which isn't such a bad thing to do because anyway, you don't want to wait forever, so it's reasonable to bound the search. Anyway, we shall come to that when we get to it. The one problem we saw last week, which you actually can run on a computer, it was the model checking problem. So the model checking, so that's, we're given a finite structure and a formula, and we see does the model satisfy the formula. So model checking is decidable. And indeed, fixed parameter tractable. So that means it's not so inefficient as long as we fix the formula. And kind of somehow collectively, these ones are impractical. Although, as I said, they are somehow the semi-decidability of validity is somehow the basis for theorem proving. So people are working on theorem provers, but nonetheless, one does not apply in general just a simple semi-decision procedure, whereas the model checking is actually practical. People do check whether models satisfy predicate logic formulas in practice. So this is practical, something one can easily write an effective algorithm for, an effective computer program for. So today we're going to spend quite a long time looking at a problem that's kind of practical in that one has applications that will do it for you, which is better behaved than these satisfiability, validity, and finite satisfiability. So today we're going to look at bounded satisfiability. So that's the question. So the input is a formula phi and a bound n. So a number bound like a number that we need to stay below, and and then the task is, so the output is yes if there exists a structure curly M such that the size of the the size is the cardinality of the underlying set, so the number of, so it wants to be a finite structure, and we want that size to be, that's not a very good less than or equals. We want that size to be bounded by n, such that the structure satisfies phi, and no otherwise. And and so essentially it's like the finite satisfiability problem. Does there exist a finite structure that satisfies the formula? Except that we stop looking at some size bound. And that, of course, makes the problem decidable because there are only finitely many, up to isomorphism, finite structures of cardinality less than or equal to n. So this problem is decidable because the computer only needs to check finitely many cases. There are only finitely many structures up to isomorphism, so we don't want to keep on looking at the infinite many different ways we can write the same structure with two elements using different names for the elements. For example, we only need to consider what each structure wants up to isomorphism. So only finitely many up to isomorphism. Put that in brackets. Or let's actually say only finitely many non-isomorphic structures. of cardinality less than or equal to n. So in principle, we could enumerate through all those structures. We just start with the structures of cardinality 1, then those of cardinality 2, and so on, just like we were doing with finite model checking, finite satisfiability last week, except that this time we know when to stop. As soon as we've exhausted all the structures of size less than or equal to n, we stop. So in principle, this can be decided. So that's have an algorithm that does the decision process. This can be decided by enumerating all such structures. Systematically, of course. But this would be very impractical. So if you tried to do that, then just as I said last week, even in small numbers, even with small n, you quickly get into very, very, very large numbers of structures, and you will be waiting a long time to get an answer. So this is an impractical approach. But nonetheless, this is not an impractical problem, because there are applications that do it, so they use a different method. They don't enumerate all such structures. So a practical approach to this the problem is to reduce it to the propositional satisfiability problem. So the one you are all very familiar with now, having done your homework, propositional SAT problem. So as you know, there are reasonably efficient, miraculously efficient SAT solvers out there. So if you can reduce a problem to the SAT problem, as we can in this case, then that's a good approach to doing it, because you can reduce it to the SAT problem and then ask a SAT solver to solve it for you. So I'm going to tell you later in the lecture how we reduce finite satisfiability, sorry, not finite satisfiability, bounded satisfiability to the SAT problem. But let's have a little interlude first and consider somehow a little example for the kinds of questions that one might look at with a finite satisfiability solver. So if we have an application that solves the finite satisfiability question, what might we do with it? So the example is a little bit unnatural, but anyway, hopefully it's good enough for illustration purposes. So it's a little bit too simple, for example, but also simplistic. But anyway, the example, I'm going to sort of revisit the network model, the axioms we had for computer network. That was in lecture 4. Oh dear. So I'm going to change it a little bit, not very much, but just a little bit simplify it and clarify a few things. So we had so there we had a binary predicate connected. So the signature, we're going to have connected. It was a binary predicate. Server and client. And these were unary predicates. They take one argument. And I'm going to have similar axioms, but not identical to before. So I'm going to have the axioms that for all x, I'm not going to write external for all x's, so that not connected. So this is a new axiom that I didn't have, I think, last time. So no server or client is connected to itself. So connected means being connected to a different machine, directly connected, say by a cable or by a direct Wi-Fi link or something like that. Then in this model, we did have this one last time, every device is either a server or a client. No device is both a server or a client, so every X is either not a server or it's not a client. Now I'm going to put in some axioms we didn't have last time. So I'm going to have that for all X, again I could miss that out because all these have for all X's in front, but anyway, if X is a client, then I'm going to require that every client is directly connected to a server. There exists a Y such that server Y and connected XY. And also in the other direction, every server is directly connected to a client. Or one I should have really put earlier that I forgot. I'll put it down here, but it would naturally go at the start, along with that X is not connected to itself, and that's the symmetry of connectedness. So for all X, for all Y, we're going to have that connected, X is connected to Y, then Y is connected to X. So the connected relation gives us a graph on the devices. A graph in the mathematical sense, that's a symmetric irreflexive relation. Here's irreflexive, here's symmetric. So connected is like the edges of a graph, which is natural because one would draw a network as some vertices for the devices and edges for the links, for the connections between them. And I'm also going to say that for all X, let's miss out the quantifiers, but they're always implicitly there. So I'm going to say that if X is connected to Y, then one of X or Y is not a server. Or equivalently, it's not, let's just say it like that. So either X is not a server or Y is not a server. So we're allowed to have clients connected to servers, and we're allowed to have clients connected to clients, but we're not allowed to have servers connected to servers. So these are the main axioms, but I'm going to be now interested in a particular situation. So the situation is that our network is big enough that for any device, there is some other device in the network that is not connected to the first device. So every device has at least one other device not connected to it. So, as soon as your network gets quite big, that's what you would expect, that some devices will not be connected to each other, and for them to communicate, they're going to have to communicate through intermediate devices. So we are interested in exploring the above axioms in the situation. So we're going to take this as a further axiom, essentially, in which also, but I'm separating it out because I think of these as the main axioms for the kind of network we're considering, and this is now more that we're adding another axiom to say we're now looking at a particular case of such networks in which the network is sort of large enough that it satisfies this problem. This not problem, this property. So the property is then for all x, so for every x there exists a y such that it's not true that x is, well, there exists a y different from x, otherwise this would be trivially true, such that x is not equal to y, and it's not, y is not connected to x. So it's not connected xy. The question I'm interested in here is, suppose we want to have as few servers as possible in the network, because maybe servers are quite expensive. Then how many servers can we get away with? So the question is it possible to have only one server? So if you want to, you can pause the video and think about this for yourself. So this is have one server in the network that satisfies this property. Now, it's a relatively simple but not totally trivial question in the case of networks with the properties that I've given. But in general, there are kind of two different ways to go about answering this question. So one is we could try to see in some way, well, if we think it's not possible to have one server, then we might try to prove the sentence that says there is more than one server. Or if we think it is possible to have one server, well then what can we do? We can try to build a model that has one server. So one could imagine that if there is a model that has one server, there should be a relatively small model that has one server, because it would be a bit funny if we could find a model that has a server and it's very large, and we couldn't find a small one, because if there's a very large one, there's nothing in these axioms to say the model would have to be very large. So one way to address this is to ask a bounded model checker the following question: find me a model or a structure such that M satisfies the property that there's only one server. So that's for all x and for all y. I'll just say for all x, y. If x and y are both servers, then x equals y. Now that's not yet a bounded model checking problem because I haven't put a bound, but let's say with the cardinality of M, I don't know, less than equal to 5, say. Very small number, but if there were one with 5 with less than equal to, if we don't find one with less than or equal to 5, then we think it's very unlikely that we're going to find a bigger such model. And we can actually submit that question to a bounded model checker. We're going to look at a bounded model checker, an actual one, practical one, in the second half of the lecture. And the bounded model checker will say, I can't find one. Or whatever outputs it gives. And this information basically makes us rather suspicious, and we begin to think that probably it's going to be impossible to find a model with only one server. And in fact, if we increase this bound, say, to 10, then it will also say I can't find one. And indeed, so actually, it is a consequence of the above axioms that the sentence, there exists an x, there exists a y, such that server x and server y and x is not equal to y. So that's actually the negation, logical negation of this sentence here. So we could actually have just proved that directly from the axioms, and it's a good little exercise to do that. As I said before, it's not completely trivial. It's a very slightly interesting argument. But in general, finding proofs is quite hard, whereas running a bounded model checker, a bounded satisfiability checker, so I say bounded model checker, but better to say bounded satisfiability, bounded sat solver. predicate logic. And really here I should say bounded sat solver. Anyway, never mind. So it's difficult in general to give defined proofs, but here we've got something automatic we can do. We can run the bounded satisfiability checker and on small numbers and see that there aren't any small counterexamples. So that does not tell us that we can prove the sentence, because there might be a large counterexample, but it gives us quite a strong in this, and a very strong in this case, because there's no reason there should be a large counterexample. So it gives us a strong expectation that actually the negation of this is provable, so that this formula is not satisfiable. This formula here is not satisfiable. Its negation here is provable. So when a bounded sat solver cannot find a solution, this gives us some reason to believe that the formula, the negation of the formula may be a consequence of the axiom. So there's a lot of mays and perhapses in here, but anyway, it does give us some reason to believe. So may be a consequence. So this is not actually science in some sense. One still needs to actually check that it really is, that the negation formula really is. So one then needs to, so if one's really principled, so one should either try on a bigger bound or then try to find the proof. So in this case, perhaps try to find the proof. So that the proof, for example, that this follows from the axioms above. Okay, there's some more constructive way. I mean, that's constructive. That's constructive. I suppose we found. So we found that we needed to have at least 2 servers, but we can also. So that's the case that we don't. The bounded model checker doesn't find any models, but we can also make use of situations in which it does find models. So continuing, so are 2 servers enough? Even if the network is quite large. Well, I'm not actually going to look at a very large network, because with a bounded model, with a bounded satisfiability checker, you can't really look at very, very large bounds, as then it won't give you an answer. But still, let's have a look. And also in this case, I want to write a formula for it. So, for example, can we find a network with say 10 devices and only 2 servers? So we can submit this to a bounded model checker. Bounded satisfiability. We're going to submit then a formula that says, can we find that says I will be satisfied, for me to be satisfiable, the network needs to have at least 10 devices and only 2 of them are servers. So we need then, there exist x1, x2, x3, all the way up to x10. And then we want that not only do there exist 10 things, but we want them to be 10 different devices. So we want to make sure that all these are different. So let's do that by putting a conjunction from I equals 1 to 9. And then an inner conjunction of j is I plus 1. Oops, I'm putting that the wrong way around. J is I plus 1 to 10. And we're going to say then that xi is not equal to xj. So this makes sure that all these 10 devices are distinct. And we want that for all, so actually this quantifier can end here, and then we want that all x for all y, or rather we want that there exists x, there exists y, such that for all z, if z is a server, it's equal to x or to y. Then there are at most 2 servers, but we've already seen that there can't be 1 server, so there will have to be 2. So for all z, if z is a server, then that implies that either z is x or z is y. And it will tell us yes. The bounded SAT solver so maybe I didn't give enough thought to what I'm calling my bounded satisfiability solver. So SAT solver looks like a propositional set. Oh, I've just drawn a squiggle on the. Looks like a propositional satisfiability solver. But anyway, when I say a bounded SAT solver, I mean a program that's solving the bounded program that's solving the bounded satisfiability problem for predicate logic. So in this case, it will tell us yes. So that means that there is a network with 10 devices with at least 10 devices. This says it doesn't stop there being more devices than this formula. It's saying there are at least 10 devices. That has only 2 servers. It's rather easy to check that for yourself, and it's rather easy to convince yourself that there are networks with any number of devices satisfying the previous axioms that have only 2 servers. But the point is, for more complicated properties than this, it might be very hard to work that out for yourself, and using a bounded satisfiability checker is an automatic way of getting an answer, so you don't need to put in the thought yourself. It will tell you the answer for you. Actually, you don't, just like with ordinary SAT solving, you don't just want the answer yes. You want to normally be given a model. So let's go back to saying what the bounded satisfiability problem is. And we'll add here so it doesn't normally just say yes. So just as with propositional satisfiability, a SAT solver will give you a satisfying assignment and output. So in this case, we expect the bounded SAT solver for predicate logic to output such a structure M. Okay. So here we're going to have a structure output. So and it will output such a structure. And sometimes it draws such things as nice pictures. So in this case, one could quite easily visualize it if it's say printed out. So we've already got 7 nodes. That would be fine, what I was drawing, but actually let's do it like this. I mean, there are so many different structures that satisfy this that one's not struggling to find them. So here we've got 7, 8, so we just need 2 more C's here. Okay, it's looking a bit like a chemical structure or something, but anyway, so there we are. So that's the sort of thing that a bounded SAT solver can do for us. So in this case, it tells us for 10, but we can explore for larger numbers and using a similar formula, and we'll always get suitable structures out. And if we did not manage to convince ourselves before that that it's always possible, whatever size of network you look at, it's always possible to find one with to have one with only 2 servers, then hopefully by seeing lots of examples, and you can often ask the SAT solver if it can find a different example as well of the same size. So one can look through lots of examples and try to understand from that. You basically get a picture of the kinds of structure your axioms are giving you. So you can learn something about what you have axiomatized by looking at example models of the axioms and the formulas that you're asking for models, for the models to satisfy. Okay, so that was sort of the motivation here. So what we want to do now is we want to actually solve bounded satisfiability by reducing it to sat. So let's go back to the black pen, which I like to write with, and so I'm going to do solving bounded satisfiability. By reducing to sat. So this is propositional. Oops. Okay. So I'm going to do this by first making some restrictions and then saying how to get around them. So we first do this for phi, so a formula in a signature with no function symbols, and also phi does not contain equality. This is not to do with the signature, but the formula phi doesn't have equality. So we'll see actually then that's not much use for the examples we've done, because this one contained equality and this one also contained equality. Well, and this one too. So we didn't have the function symbols in the example, but the not containing equality doesn't allow us to do what we've just done. But at the end, we're going to say also how to deal with equality. So what I'm going to do is I'm going to add, well, so let n, so phi is the input formula. So the input formula is phi, and the bound is n. So first, I extend the first order signature, the signature of predicate logic, by adding some constants. So first we add n constants. So remember they're constants as zero arity function symbols. So we add n constants, which I'm going to call little c1 up to little cn, to the signature. So this is to the first order signature, the signature of predicate logic. Okay, so having done that, we also want a signature, as it were, for building the propositional formulas. So that means we need to say what the propositional atoms are. So for propositional logic, well, let's say it like this: we build propositional formulas And to say how we build the propositional formulas, I need to say what the propositional atoms are. Using as propositional atoms the following. So for every for every predicate symbol in the predicate logic signature, every predicate symbol of arity. So let's give the predicate symbol a name of arity K, say. So that's the arity P. That's the arity of the symbol P. We add a propositional constant, a propositional atom, which I'm going to call again P, but let's write it a bit smaller, but it's kind of, the name is given from this P. And it's going to have K little indices here. So for every K tuple, I1 through to IK, from the set 1 to N. So the idea is we're bounding the size of the structure by N, so the elements of the structure can be labelled 1 through 1 up to N. Some of these labels might denote the same element of the structure because we're not guaranteed to have N different elements in the structure. We just got at most N elements there, but nonetheless we can distribute the labels 1 to N over the elements of the structure. And the idea is these little indices here, this K tuple is then giving us a K tuple of elements of the structure via their labels, and this propositional atom is going to say the same thing as saying that the predicate P holds of that tuple of arguments I1 through to IK. And that's it. So just for every predicate symbol of arity K, we then add K to the power of N, because that's how many there are propositional atoms for that corresponding to that predicate symbol. So the signature is getting quite large, but still we can deal with it. So what we want to do now is I'm going to define a mapping from sentences we define a mapping phi to, I'm going to call it phi star, from predicate logic sentences in the extended signature with the constants to propositional formulas. Using these propositional atoms. So I'm just going to define this by saying what it does on certain chosen logical constructions. So let's begin with maybe the most interesting cases, which are the quantifiers, but actually I will only do the existential quantifier. So there exists x phi. If we star that, we need to convert that to this predicate logic formula to a propositional formula. So what we do is we consider, so this is defined to be equal to so we consider formula phi with the new constant symbol C1 substituted for x. That's now, this was a sentence, so it only has, phi only has the free variable x. Exists x phi has no free variables, so phi itself has at most the free variable x. So if we substitute C1, the constant C1 for x, we again get back a sentence. So we can translate that. We're now translating a logically simpler sentence because it no longer has the existential quantifier. And we consider that, or phi with C2 for x. We translate that, or all the way, of course, until we have phi with Cn for x. And the idea is kind of obvious, really, because we're saying there exists an x such that phi, and then we know that our structure contains at most n elements. We're in the first order logic extended signature. The point of these constants C1 up to Cn is to refer to the labels of those elements. So exists x phi is saying either phi holds for the element labeled by C1, or it holds for the element labeled by C2, or and so on, or it holds for the element labeled by Cn. Since there are at most n elements, we name them all in this way. If we consider, say, disjunction, why not a disjunction? No, let's do a conjunction. It really makes no difference. Phi or psi. If we translate that, well, we just translate phi to a propositional formula, and we translate psi to a propositional formula. Similarly, if we translate not phi, then we translate phi and negate it. So we do the translation there and negate it. And for atomic formulas, well, we don't have equality because I've assumed that we don't have equality in the formula. So we only need to translate P of, and we don't have any function symbols. So the only terms we have are variables and the constants we've added to the signature, these C1 up to Cn. But because this is a sentence, it can't contain variables. When the predicate symbol, any variable inside is going to appear free, so it wouldn't be a sentence if it had variables. So this is going to be some Ci1 up to Cik. So we've got some P has arity K, and then we must have, its arguments must be K of these constants, and we just translate that to P with the indices I1 through to Ik. So P, a predicate symbol of arity K. And the universal quantifier, well, you could translate it using that for all x is the same as not exists x not, so we've got the recipe here, or you can think for yourself what it should be. So that's a little exercise for you to write it out in simple terms. And the same with disjunction, implication if you want. Anyway, this is the translation. I'm going to, in a moment, state the result that says that the translation is correct. Just let me remark one other thing, that it's a recursive definition of a function, so it's perfectly easily definable as a computer program. One writes in the syntax for the predicate logic formula. The recursive program will churn out the syntax for the propositional logic formula, so it's perfectly programmable. Notice at each case we're defining the translation on a more complex logical formula by reducing it to translations on simpler logical formulas. So here we've lost the existential quantifier, here we've lost the conjunction, and so on. And the propositional, the result that says this is correct is that following proposition which is phi is satisfied by a structure M of cardinality less than equal to n, if and only if the propositional formula phi star is satisfiable. And that's rather evident from the definition. So I already basically talked you through why the exists X case, the existential quantifier case, is correct, and similar arguments apply in, and easier, in fact, arguments apply in all the other cases. And so we notice, well, that so we have a reduction to propositional logic, and we then get a formula that we can submit phi star to a SAT solver. So let's write this down in more detail. So suppose let's write a bit more neatly. Suppose we have axioms let's say so phi 1 through to phi m, so m axioms, predicate logic, and we want to show that phi is satisfied by some structure or some model of the axioms. So by that I mean that phi 1 to phi m all hold in the structure. This is little m, and this is the big curly M that's the structure. So this is, so let's put it with the cardinality of the underlying set. So the cardinality of this is less than or equal to n. So this is the case we were in our example, that we had some axioms. Where are they? Here we had some axioms, and we wanted to check whether a particular sentence is true in some model of the axioms, in which the axioms hold. Then we submit we basically want to find out if the conjunction of phi1 up to phi little m and phi is satisfiable. So we translate that to a propositional formula using the Tsatsin translation. To convert to CNF, the conjunctive normal form, if necessary. Let's say if necessary on the slide, not the slide, the notebook, or whatever. If necessary. And yeah, now we submit this to a SAT solver. And that way we solve the bounded satisfiability problem practically, because this is something we can actually do. But there are two little extensions. So one is to deal with function symbols, and the other is to deal with equality. So let me treat them one at a time. So in the case the signature has function symbols, what we do is we replace it by a signature that doesn't have function symbols. So we use predicate symbols in place of function symbols. And then we can apply the method before. So we replace every function symbol f, say, of arity k. So if f is of arity k, then we will do this for arity k, and if g is of arity L, we'll do the same thing for arity L, but I'll just illustrate it in this case. If f of arity k, so we replace every function symbol with a new predicate symbol. Pf of arity k plus 1. And the point is this predicate symbol expresses the relation known as the graph of the function. So we add together with axioms and the axioms say for all x1 through to xk, there exists a y such that pf x1 xk y. So that's saying the relation at least returns a value for every tuple of inputs to the function, and we also want to say that function is unique. So then we say for all x1 through to xk and for all xy, let's make that yz just to make it clearer. And we can just keep this on the end of the list of things being universally quantified. So if pf and pf x1 to xkz, then y equals z. So this says if the function can only take one value on the tuple x1 to xk of arguments, because if it takes the value y and the value z, then they're equal. Notice that here we're using equality, so we're still going to need to get rid of the equality. But the point is we add these axioms that say that we have a functional relation pf here, and then we can use the relation pf wherever we have a function symbol, and then we translate, and I'm not going to explain how to do this, but it's not hard to do it in practice. We translate axioms or formulas in general involving the quantifier, involving the function symbol f into equivalent formulas involving the predicate symbol pf. So e.g., if q were a predicate symbol, the q of f of x translates to q of y, or even exists a y, q of y, and pf x y. And this can be done for any formula involving f. So this gets rid of the function symbols, but it introduces equality symbols, and we also in any case might want to be dealing with formulas involving equality symbols. So then the last step is to eliminate equality symbols. So we finally eliminate function eliminate. We don't eliminate them, sorry, this is the wrong word. We finally deal with equality by just treating equality as a predicate symbol, which is what it is. It's just not a predicate symbol in the signature. Equality as a binary that's of arity 2, a binary predicate symbol. So we can just then do the procedure that we did here for signatures with only predicate symbols. But we need to then add further axioms saying that the equality predicate behaves as equality. So we treat this and we add, and adding the axioms. So for all x, x equals x, so the axioms that say that equality is an equivalence relation. So that's the reflexivity, symmetry, transitivity, and lastly, a whole set of axioms saying, which are also the other important property of equality, which is its substitutivity property, that if you've got two equal things, then any two equal things are as good as either one is as good as the other in any formula, in any relation, and we can just state that for the relations stated by the predicate symbols in the signature. So then, and for every predicate symbol P, of arity K, axioms for all x1 for all xk, well, let's just write it x1 through to xk. We want to say that if xi let's do it like this, and for all yi, if xi equals yi, then p of x1 through to xk if xi equals yi and p of x1 through to xk holds, then the same thing holds, then p holds if we replace xi with yi. So then p holds if, let me write it in, of course we might not have this many arguments, but I hope you can see what I mean. So we replace only the ith component with y. So we have this for every one axiom. So we have one axiom for every p, and again, for every p we have not just one axiom, but we have k axioms. So this is k axioms. K axioms 1 for every I in the set 1 through to k. So every possible argument position of p. And of course, this is saying in every argument position, if we get something else equal to it, then p holds for the tuple with xi. If that holds, then it also holds for the tuple with yi. And the implication only needs to be in one direction, because this axiom implies the implication in both directions. and we need one axiom for every position I, some of you might be quick and you might think, why don't we just say, why don't we give ourselves y1 through to yk here and put a conjunction x1 equals y1, x2 equals y2 and replace all the x's and all the y with all the y's, and you can do that. But if we do that, that gives us some additional quantification here, and because of how we translate formulas into propositional logic, one tries to make the length of quantifications as short as possible, because every additional quantification was expanding the formula, duplicating the formula essentially by the multiple given by the capital N. That's the bound we're using for the bounded satisfiability. Okay, so this actually basically ends the translation. So having done this, so finally, having dealt with function and equality symbols, we apply the star translation from earlier, which we can apply because we don't have any function symbols now, and equality is just treated in the same way as every other predicate symbol. Okay, so I think that's enough for the first part of the lecture. In the second part, we're going to look at a piece of software that actually does bounded model checking. Okay, so bye for now, and be back shortly.